In the previous section, we looked at estimating a population proportion. In this section, we're going to look at estimating a population mean. But a lot of the techniques are going to be analogous to what we looked at in the previous section, but some of the calculations will be slightly different. If we were trying to estimate a population mean without knowing the population standard deviation, which is almost always the case, normal distributions have too much unreliability, especially for small sample sizes. So before, we would get a z-score, and we found that the z-scores for the population mean, or rather for the sample mean, are normally distributed. And so we were able to use our normal distribution. However, we're not going to be using this anymore because we don't know the population standard deviation. So we're actually going to look at what we call a t-score, and this is going to follow a t-distribution. So it's very similar. The main difference is in the denominator, instead of dividing by the population standard deviation, we're dividing by our sample standard deviation, which is itself divided by the square root of the sample sizes. Let's take a look at our t-distribution chart. If you need a copy of this, you can find one in the modules section under Canvas. So what we have here, notice these first two rows, we have area in one tail and area in two tails. For this section, we're mainly going to be concerned with the area in two tails. So if you recall in the previous section, when we had a 98% confidence level that we were dealing with, that left us with 2% to distribute between the tails. If you looked at a t-distribution, it would look very similar to a normal distribution with two tails. And so a 98% confidence level would have 2% in the tails, which corresponds to 1 in just one of the tails. So in this section, again, we'll be mostly concerned with the area in two tails, and in the future we'll talk about, or we'll be using, the area in one tail row. So what this does is once I've figured out the area in two tails based on my confidence level, once I've figured out which one of these I'm in, that tells me which column to look in for my t-score. Now we'll talk about this degrees of freedom column in a second, but the way to figure out where you are in that column is calculate the degrees of freedom for whatever your sample is, and that'll tell you your t-score. Okay, let's look at some examples. Given a sample size n, for simplicity's sake, we calculate the degrees of freedom to be n minus 1. So suppose we take a random sample of 12 Guinnesses from a factory, calculate the degrees of freedom for this sample. Well, of course, 12 minus 1 gives us 11, so we have 11 degrees of freedom for this sample. Suppose a sample size 7 is a simple random sample selected from a normally distributed population. Find the critical value, t alpha over 2, corresponding to a 95% confidence level. So first of all, let's calculate the degrees of freedom, because we'll need that when we look at our chart for our t-distribution. So the degrees of freedom here, since our sample size is 7, we get 7 minus 1, which is 6. So to calculate our t sub alpha over 2, or in other words, 0.025 to the right of this t-score, we need to look at that t-distribution table. Now I put 0.025 down here to indicate that whatever t-score we come up with, it would have 0.025 to the right. However, the nice thing about the t-score table, the t-distribution table rather, is that it tells me in two tails it would have 0.05. So let's take a look at the table. So I need to find the column that corresponds to a 95% confidence level. To do that, I said it was a critical value would have 0.025 to the right, but since it's 95% and this t-distribution table does the calculation for me, I know it's going to be 0.05 in 2 tails. So that means I'm in this middle column here. So all I need to do is find my degrees of freedom row. And we said the degrees of freedom was 6. So I'm going to be in this middle row, in the 6th row here, in the middle column. That means my critical t-value is 2.447. So we found our critical t-value to be 2.447. Now, just like with proportions, we're going to calculate the margin of error for our estimate of the population mean. It's a similar calculation, but of course, instead of multiplying our critical z-value, we have a critical t-value. And now, instead of a p-hat and a q-hat, we have a sample standard deviation that we're going to divide by the square root of our sample size. So let's try this example. Assume we collected a random sample of 49 subjects to measure the effects of a cholesterol-lowering drug. You find that this sample lowered the mean cholesterol level by 0.4 points and had a standard deviation of 21 points. Calculate the margin of error for a 99% confidence interval. So first of all, let's calculate the degrees of freedom. Since there are 49 subjects, our sample size is 49, which makes our degrees of freedom one less, that is 48. Now we want to calculate the critical t-value for a 99% confidence interval. So this will be the t-value associated with 0.01 in 2 tails. So looking at our table, we're looking for the column that has 0.01 in 2 tails. And of course, that is this left column here. So now I need to go down and find 48 in my degrees of freedom row. The problem is there is no 48. It starts jumping once you get past 40. The reason for that is the difference between your t-values is not so great once you get above 40. So I'm looking for degrees of freedom 48. I'm just going to pick the degrees of freedom closest to 48, and that'll be the critical t-value that I'm going to choose. So we're going with 2.678. So we found our critical t-value to be 2.678, and now we want to use this margin of error formula to calculate our margin of error for the confidence interval 99%. So I'll plug in my critical t-value that I found. The standard deviation for this sample is 21, and I'm going to divide that by the square root of my sample size, which is 49. Throwing all this into the calculator, I get 8.034. Now that's kind of a surprising result, but we'll look at why that is in a second. So now let's talk about constructing a confidence interval. It's constructed in the same way that we did for estimating population proportion. That is, we're going to take our sample mean and subtract the margin of error to get the lower estimate, and we're going to add our margin of error to our sample mean to get the upper estimate. And that will be an estimate of the where our population mean lies between. So if we're looking back at this example, this time we want to calculate a 99% confidence interval and interpret the results. So that is, we can use all the same information we calculated before. The one thing we're going to do different now is calculate this confidence interval. So same degrees of freedom, same critical t-value, and the same margin of error. To calculate my confidence interval, I'm going to take my sample mean and subtract off the margin of error for my lower estimate. Then I'm going to take my sample mean and add the margin of error for my upper estimate. So this gets me that I estimate my population mean to be between negative 7.634 and positive 8.434. That is, the mean amount of raising or lowering, or I should say, the mean amount that this cholesterol-lowering drug would lower somebody's cholesterol, I'm confident it's between negative 7.634 and 8.434. Since 0 is in this interval, it is possible that this drug does not lower cholesterol at all. In other words, it could be that the mean amount this cholesterol drug would lower somebody's cholesterol is 0. In other words, this drug may be ineffective. And that's what this confidence interval is telling us. So even though our sample had a mean lowering cholesterol by 0.4 points, our confidence interval suggests that maybe that 0.4 is not significant enough to say that this drug actually has an effect. So just to review our steps in calculating confidence intervals for estimating population means, you first calculate the degrees of freedom by your sample size minus 1. Then you want to find your critical values using the t-distribution table. Then you want to calculate the margin of error using the margin of error formula for estimating a population mean, which is different than the margin of error formula for estimating a population proportion that we saw in the previous section. And finally, step 4, you want to calculate the confidence interval by adding and subtracting that margin of error to your sample mean. So let's look at another example. In a study to test the efficacy of using magnets to treat back pain, 40 patients were given a treatment with magnets and also a sham treatment without magnets. Pain was measured on a scale from 0 to 100. After being given the magnet treatment, the 40 patients had pain scores with a mean of 11 and a standard deviation of 2.5. After being given the sham treatment, the 40 patients had pain scores with a mean of 10.6 and a standard deviation of 2.1. First, let's construct a 90% confidence interval estimate of the mean pain score for patients who were given the magnet treatment. Then we'll construct a 90% confidence interval estimate for the mean pain score for patients given the sham treatment. And finally, we'll compare the results and ask the question, does the magnet treatment appear to be effective? So first of all, we need to calculate the degrees of freedom for this sample. If our sample size was 40, then our degrees of freedom will be 39. The next thing we'll do is calculate the critical t-value. We're calculating a 90% confidence interval estimate of the mean pain score. So 90% means that there's 0.1 in two tails. So go to your t-chart and see in the 0.1 in two tails column, can you find 1.685 at the 39 degrees of freedom row? Then from there we can calculate our error estimate, or our margin of error, as 0.666, and finally we can add and subtract that 0.666 to our sample mean, which in part A, if we were looking at the patients who were given the magnet treatment, the mean score was 11. So I simply took 11 minus 0.666 and 11 plus 0.666. So let's do the same thing for these folks who were given the sham treatment, who reported a mean of 10.6 and a standard deviation of 2.1. Well, they're going to have the same degrees of freedom and the same critical t-value. The margin of error will be different because standard deviation is different. So they have a margin of error of 0.559. Now taking that margin of error and adding and subtracting it to their mean, that is the mean of 10.6, we get an estimate of the population mean to be 10.041 to 11.159. Now comparing these results, notice how the intervals overlap, and by quite a bit. So since the confidence intervals overlap, it appears the magnet treatment is no more effective than the sham treatment.